good morning friends. I am Vaishakhi Shah from LJ Institute of Engineering and Technology. In our subject Fluid Mechanics and Hydraulics, we started our module which is flow measuring devices, and in last lecture we studied orifice, which is used for measuring the discharge. Now in today's lecture we will discuss another device which is used for measuring discharge, that is mouthpiece. As we know that orifice is used to measure discharge, same way mouthpiece is also used to measure a discharge of the fluid. Now first, what is mouthpiece? Sometimes with orifice is a opening provided in water tank. So sometimes with that opening a short pipe is fitted which increase the value of coefficient of discharge. If you see somewhere, then in with opening some short length pipes are provided, and the intention for that pipe providing is to increase the coefficient of discharge. Now we know that the increase the value of coefficient of discharge will increase in the discharge through the orifice. If coefficient of discharge increases, then discharge from orifice also increases. So such a pipe whose length is generally more than 2 times its diameter of the orifice, and it is fitted externally or internally to the orifice, which is known as mouthpiece. So mouthpiece, the length of mouthpiece is generally 2 times the diameter of the orifice. As you can see here that there are small pipes which is fitted with the orifice, and this small length pipe is called mouthpiece. Generally it is placed with orifice to increase the amount of discharge, and mouthpiece is used to measure the flow of the liquid. Clear? So again, in simple word, mouthpiece is a short length pipe which is connected with orifice to increase the amount of the discharge. Okay. Now there are some types of mouthpieces, where first theory is classification of mouthpiece. So depending upon shape, mouthpiece is classified as cylindrical mouthpiece, convergent mouthpiece, convergent divergent mouthpiece. So first of all, according to shape, first is cylindrical mouthpiece. Okay. Second is convergent mouthpiece. In a convergent mouthpiece, the diameter of pipe is decreasing. This type of mouthpiece where diameter of pipe decreases, that is called convergent mouthpiece. And third is convergent divergent mouthpiece, where first diameter decreases and then diameter increases. The pipe where first diameter decreases again increases, that is called convergent divergent mouthpiece. Okay. Now second type of mouthpiece is according to nature of discharge. At outlet, mouthpiece are classified as mouthpiece running full. If your pipe is running full, your fluid cover all the area of the pipe, then it is called mouthpiece running full. And it is partially filled or partially empty, then mouthpiece is called mouthpiece running free. Okay. Next type is depending upon position with respect to tank, they are classified as external mouthpiece and internal mouthpiece. So as you can see in this diagram, the first diagram, the mouthpiece is placed with orifice in a water tank. This opening in water tank, the opening in water tank is called orifice, and we connect a pipe, this pipe with opening, that is your mouthpiece. So as in first diagram, as you can see, the pipe is connected inside the water tank, so that is called your internal mouthpiece. And here the pipe is connected from outside the water tank. Pipe is connected from outside the water tank, which is called external mouthpiece. Clear? So difference between external and internal mouthpiece, it is simple. Internal mouthpiece is connected from inside the tank and external mouthpiece is connected outside the water tank. Okay. So now our first derivation, which is flow through an external cylindrical mouthpiece. As we know that external mouthpiece, the mouthpiece which is connected outside the water tank, that is external mouthpiece. So here is the image of the external mouthpiece. As you can see, this is your water tank, this is your mouthpiece. Now mouthpiece is connected externally. It is connected externally with water tank, outside of the water tank. Now if you are taking this line as a center of the pipe, center of the mouthpiece, so from center, the water level in a tank, the height between center to water level, which we indicate as small h. You can clearly see the height between center of the pipe to free surface is small h. Now the another thing you have to remember in this diagram is when fluid enters into the mouthpiece, first of all it contracted, after that it expands. When fluid enters, we already studied the theory of vena contracta. So when the fluid entered to the mouthpiece, at first it contracted, after that fluid expands. So the section where maximum contraction occurs, that is called CC, which is your vena contracta. As you can clearly see this section CC, where maximum contraction of fluid occurs, that is called vena contracta. Okay. Now area of fluid at vena contracta is AC. Now from section BB, this section is your BB. From section BB, the fluid comes out from the mouthpiece. From here, fluid exits from the mouthpiece, and the area of fluid at section B is small a. Area of fluid at section CC is AC. Clear? Okay. CC is called vena contracta. Now, as we know that mouthpiece, area of mouthpiece is small a. Area of jet at vena contracta is AC. Weight of the liquid, height of the liquid is small h. Absolute pressure at BB and water surface. Now here at BB, the water comes out from the mouthpiece. So here water comes into contact with atmosphere. Remember that when water comes out in a contact with atmosphere, so at section BB, at here the pressure is atmospheric pressure on the water. Okay. Now at section CC, the pressure head we indicate as HC, and at section BB, the pressure head is HA. HA is your atmospheric pressure head, and head loss through the mouthpiece is HL. Here there is some amount of head loss here, which is HL. Now velocity at vena contracta is VC, and velocity at B is V. Velocity at vena contracta VC, velocity at B is V. Okay. Now let's start the derivation. Applying the Bernoulli's equation between free surface of the liquid. Remember that here we will apply Bernoulli's equation 2 times. First, you have to apply Bernoulli's equation at, you can see the free surface of the liquid where water level is written. So first you have to apply Bernoulli's equation at free surface of the liquid and section BB. Here is your section BB and there is your free surface of the liquid. So you have to apply Bernoulli's equation at section BB and free surface of the liquid. So Bernoulli's equation, if you remember, we already studied. Bernoulli's equation is P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g plus V2 square by 2g plus Z2. Now, first on left hand side, there is P1 by rho g. P1 by rho g. So, first we applied Bernoulli's equation at free surface of the liquid. Okay, P1 by rho g. So, that is pressure head. Now, on the free surface, the atmospheric pressure is acting. So, on the free surface of the liquid, P1 by rho g is replaced by HA, which is atmospheric pressure head. We know that P by rho g is H. So, here P1 by rho g is replaced by HA because on the free surface atmospheric pressure is acting. So, P1 by rho g equals to HA, atmospheric pressure head. Okay. Now, second is V2 square by V1 square by 2g. Velocity at free surface is 0. So, here V1 square by 2g equals to 0, V1 equals to 0. Now, third term in Bernoulli's equation on free surface, which is Z1. Now, height from center to free surface is small h. So, here Z1 equals to h. This is a Z1, height of center of the orifice to free surface, which is small h. So, on the left hand side, on the free surface of the liquid, the Bernoulli's equation is HA plus H. Clear? Now, on right hand side, at section B, at this section, the Bernoulli's equation is P2 by rho g, P2 by rho g. P2 by rho g here is again a atmospheric pressure head, which can replace by HA. P2 by rho g equals to HA plus V2 square by 2g, or you can say V square by 2g. Okay, clear? Plus the center line here, the center line we taken as a bottom line. So, here Z2 equals to 0, Z2 equals to 0, and there is a head loss between section CC to BB. There is a head loss at section B, which is HL. Head loss at section B is HL. Clear? So, we applied Bernoulli's equation at free surface of the liquid and section BB. This is your equation number 1. Now, similarly, apply Bernoulli's equation at free surface of liquid and section CC. Now, section CC is your vena contracta. So, applying Bernoulli's equation at free surface of the liquid, which is HA plus H. We already applied Bernoulli's equation on free surface, which is HA plus H. And now, Bernoulli's equation at CC is P2 by rho g, that is your HC, at pressure head at section CC, that is HC, and Vc square by 2g. Velocity at section C is Vc. So, Vc square by 2g. Now, HA, H equals to Hc plus Vc square by 2g. This is your equation number 2. Now, compare equation 1 and 2. So, you get HL equals to V square by 2g bracket 1 by Cc minus 1 square. Here you can replace AC by AC by A with Cc, where Cc is coefficient of contraction. So, your equation of HL become V square by 2g into 1 upon Cc minus 1 whole square. Okay. Now, we know the equation number 1, which is HA plus H equals to HA plus V square by 2g plus HL. Now, we know the equation number 3, which is H equals to V square by 2g 1 plus 1 upon Cc minus 1 whole square. This is your equation number 3. Now make H from equation number 1 as a subject. Here H is your subject, so equation become V square by 2G bracket 1 plus 1 by Cc minus 1 whole square, that is your equation number 3. Now we know that equation for theoretical velocity under root 2gh. We already derived the equation for theoretical velocity. V theoretical equals to under root 2gh. Now we know the equation for coefficient of velocity, which is Cv, that is area at vena contracta by area at orifice. Actual velocity by theoretical velocity. So here actual velocity equals to Cv into theoretical velocity. So here equation for velocity is Cv into under root 2gh. Now substituting value of V in equation number 3, we know H equals to V square by 2G. So if we place the value of V in equation number 3, you get Cv equals to 1 upon 1 plus 1 by Cc minus 1 square raised to 1 by 2. This is a formula for Cv. Now we also know that CD, that is coefficient of discharge, CD equals to Cc into Cv. So if we place the coefficient of discharge CD equals to Cc into Cv, so discharge through mouthpiece can be written as Q equals to CD into small a into under root 2gh. That Q is your discharge, CD is coefficient of external mouthpiece, small a, that is area of the mouthpiece, under root 2gh. H is height of the liquid. So this is a final equation to find out discharge from external cylindrical mouthpiece. Now we will solve an example based on this theory. So find the discharge from 100 mm diameter external mouthpiece fitted one side of the large vessel if head over the mouthpiece is 4 meter. In this external mouthpiece of diameter 100 mm is given to you and head over mouthpiece is 4 meter. So diameter small d is 100 mm and head over mouthpiece is 4 meter, small h equals to 4 meter. Now we know the equation Q equals to CD into A into under root 2gh. So in this equation, in this example, diameter is 100 mm. If you convert into meter, then it is 0.1 meter. H equals to 4 meter. As we know that area small a is pi by 4 d square, we know the value of diameter. So placing small a equals to pi by 4 into 0.1 square. So your answer for A is 0.0079 meter square. Now discharge through external mouthpiece Q equals to CD into A into under root 2gh. Now remember this, for external mouthpiece, for external cylindrical mouthpiece, this CD, value of CD is 0.855. You have to remember these values for external mouthpiece only. For external mouthpiece, the value of CD is 0.855. So Q equals to 0.855 into A into root 2gh. Now 0.855, the area is 0.0079 into under root 2, 9.81 into 4. So your final answer for discharge Q is 59.5 liter per second. This discharge is from external cylindrical mouthpiece, and remember the value of CD, coefficient of discharge, for external mouthpiece only, that is 0.855. This value can be changed for internal mouthpiece. Okay. So done for the today, and in now next lecture we will discuss some other theories based on mouthpiece. Okay. Goodbye.